Hi, my name is Brian Heck. I am a solar system ambassador, and I am also connected with the Wings of Freedom Aviation Museum in a couple of different roles. Today I'll be acting as a docent, taking you on a virtual tour and a discussion of one of our aircraft, the Seadart. Specifically, we'll be talking about the rule that killed the Seadart, and that rule is called the area rule. The Seadart's a beautiful aircraft. It was the result of a request by the Navy for a waterborne fighter interceptor. Convair developed this aircraft, leaning heavily on its previous success with the F-102 Delta Dagger. The two aircraft have much in common. But right now I'd like to just point out a couple of things that are different about the two aircraft. First off, the air intakes on the aircraft are up on the top of the fuselage and moved to the back. Obviously, it doesn't have landing gear. It's got skis, and it's a twin-engine aircraft rather than a single engine. It had a lot in common with its predecessor at Convair, both aircraft developed by the Convair Corporation. The Delta Dagger was a recent success for Convair. The Air Force bought lots of them, and it was an interceptor that was intended to do Mach 1 plus, but came up a little short. And it was because of that that some research was pushed into why, and this idea called the area rule, which I will explore now, came about. But as you can see, the two aircraft, in simple plane form, have a lot in common. But the big difference between the two is the air intakes and the fact that the Dagger had a single engine, whereas the Delta Dart had two engines. Here is the YF-102, the prototype for the 102. It's a little different than what the aircraft that went into production. Notably, the canopy is different, but for our purposes, the main difference is right here in the fuselage. The YF-102 fuselage is shaped like a tube, whereas the later aircraft, there's a bit of a change, and we'll get into that in just a moment. So here is the plan form of the YF-102. As you can see, the lines of that fuselage are very straight, and we're going to see that that causes problems in the long run. As the aircraft moves through the air, and you're talking about close to the speed of sound, the fact that the sound barrier is caused by the fact that the air molecules, as they are attacked by the aircraft, just simply do not have time to move out of the way. So they kind of pile up in front of the aircraft, and they cause what is known as a shock wave. This shock wave then disrupts airflow over the aircraft from that point aft. Often what this means is a loss of control and stability for the aircraft, and usually it kind of ruins the pilot's day. As we can see here, the Seadart has a similar plan view. Again, we have this straight body line right here that I want to emphasize, and the delta wing. Obviously, this aircraft is designed for high-speed flight. So when we have that kind of straight fuselage, as you can see on the left diagram at the top, this is a cross-section of hypothetical aircraft. What that dictates, that shape, is that we have this cross-sectional area graph below. And as we move from the front of the aircraft to the back, and that would be from the left to the right, the cross-section, or the area that faces the incoming air, increases as the aircraft moves back. So our largest cross-sectional area is right there about mid-wing as we move across the aircraft. It's the area of greatest transonic drag. And what that means is that from that point back, airflow is disrupted. Perhaps aerodynamic controls won't work any longer, and we have the possibility of negative reaction to the aircraft. So to counter that, all we need to do is fix that area. Right here we see that fuselage right in that yellow area on the YF-102 is where the cross-sectional area is at its greatest. So let's decrease. Same problem we have with the Seadart. Right in that area there where we don't want it. Because imagine that at that point right there in the center of that oval, in a line moving across the aircraft laterally, the shock wave is going to build up, and from there backward we have disrupted airflow. We have uncontrollability. We have potential for serious problems. So you can see the red line indicates the area where the cross-sectional drag would be at its greatest. In the traditional old tube-shaped aircraft, we have that bump right there where the red line is. As we do what's called an arearule or Coke bottle, the body of the aircraft, we see that bump is smoothed out and a much lower maximum cross-sectional area by simply cinching in, if you would, the waist of the aircraft. And it causes much better transonic aerodynamic behavior of the aircraft. Here we see how much less, you can see by the green line, that the cross-sectional area or the overall drag of the aircraft is significantly decreased. This is enough to decrease in drag to change the F-102 as a prototype as a non-sonic capable aircraft to the production F-102s were capable of supersonic speed in the low Mach 1 plus range. So this next diagram shows us a little bit different perspective on the same idea. On the left we have a traditional aircraft. The blue box area you see is a straight fuselage. The wing is at its greatest width there. So therefore we have in that red bump, that red circle, we have a bump in the overall cross-sectional area that equates to an overall maximization of drag. On the left we have an aircraft that has had bulges put in the rear but an indent fuselage at the wing. This greatly decreases cross-sectional area, thereby greatly decreasing the drag on the aircraft, allowing the aircraft's performance to be improved. So here is the improved F-102A with the slight change in the waist of the aircraft or the fuselage. You can see a slight indentation there in the yellow area. This was just enough to bring that bump in the cross-sectional area down. So here we see the planform of an F-106, the follow-on aircraft, the F-102, built by Convair. Both aircraft were intended to be high-speed interceptors. This aircraft was much more capable than the F-102. In fact, this aircraft could fly fast enough to burn the paint off of itself. Showed just the difference. Well, the engines were different, but the decrease in drag by the refinement of the arearule is really noticeable in the evolution of the Delta wing aircraft built by Convair. So we have to say, what if the arearule had been applied to the Seadart? Well, it wasn't, so that's what killed the program, in my mind, ultimately. There are other factors. We could discuss at another time, but I think that without arearuling, the aircraft was fundamentally unstable, had very, very high transonic drag characteristics, and therefore made it very unlikely to have ever fit the purpose that it was built for, which was a supersonic fighter interceptor. So it was a done deal. So we never see lots of these ads in newspapers extolling young prospective pilots to become naval aviators and climb into their Convair-built Seadarts and go off and defend freedom. Thank you for watching my little program today. I hope you enjoyed it. I found it interesting and hopefully informative. I am the sole author of this presentation, and I made a valiant effort to make sure that all of the pictures that are in here are in the public domain, or that I have releases to use them. All the material that I've displayed has been sincerely researched for accuracy, and I reserve the right to all this material. Questions should be sent to me at brianpheck@gmail.com. That's all one word, brianpheck@gmail.com. We have some upcoming programs on Facebook. We'll be posting them. Look out for these other programs. Project Mercury's Golden Winged Astronauts. That's all about the first 4 naval and marine pilots that became astronauts. Project Mercury's Silver Winged Astronauts are about those other 3 of the first 7 astronauts. They were Air Force pilots prior to NASA enlisting them. And then finally, we have a program I'd like to call Aircraft Evolution 1930-1980, where we'll be looking at how aircraft have changed over the years, specifically focusing on the aircraft at the Wings of Freedom Aviation Museum as our examples. So that, and we'll be doing much more in the future. Hope to see you at the Wings of Freedom Aviation Museum very, very soon.